Hello, yeah, so I'm Julian. I lead the formal verification team at Nethermind, and I'll start off by saying that there are a couple of small typos in the slides, which I'll sort of point out as we go along. And this is the most important one, which is that I actually put the wrong Nethermind logo there. It's actually this one, and yes, it's totally different. There are small gaps between the segments. So anyways, I got told off about that, so I thought I'd point that out. Basically, to give an overview of the goals of this talk, it is basically to point out that, well, Ethereum secured 74 billion in assets. There's about to be this massive protocol change that Will talked about earlier today to what we call lean Ethereum. And we're going to talk about another lean thing in a second, which hopefully they won't get another cease and desist letter from the Lean Foundation. We'll cover what lean is in a second, but it predates what the sort of like lean Ethereum concept. But we'll get into that in a second. The point is, there's this big change happening. And obviously now the protocol is such that it relies on the correctness of these ZK protocols, these SNARKs, and these things rely on mathematics, which are too complex for me to be able to like grab someone off the street and explain it to them very quickly. It's reached a level of complexity, both the consensus protocol and then also the execution layer has now reached a level of complexity where it's no longer sort of like the mathematics involved in it is no longer trivially auditable by a random person with like high school or even like bachelor's degree mathematics background. All of this is of course really to be able to achieve the scaling that we want to be able to have Ethereum be this sort of like underlying layer for like the global economy. And obviously, as we said, as we know from the previous talks, the solution that Ethereum is going for is the zkVM approach, which allows us to not have to basically rerun each one of our transactions, and allows us to basically just check this cryptographic proof that allows us to verify that the state update is correct with high probability. So I'm going to start off with a tiny warning, which is that this talk is going to use the word proofs in two ways. So there is a nature of a cryptographic proof, which is a probabilistic proof. It tells you that something is true with very all but negligible probability. And then there's a sort of like a logical or mathematical proof, which is, well, based on some axioms and some inference rules, you prove a statement is correct, right, with respect to these rules. Two kinds of proofs here. Hopefully that won't get too confusing. It's very confusing when my team works on it, but hopefully we'll get through that. Perfect. Okay, so now to understand what is, what do we actually need to formally verify to have a full formal verification of essentially what we'll call the beast mode part of this. So the execution layer part of the lean Ethereum transition, we're going to want to look a tiny bit at the like very high level architecture of a zkVM. A zkVM typically at a high level has this kind of a structure, right? So we have here what we call the constraint system for an ISA. That's an instruction set architecture. There's a comma missing. That's one of it's Risc5, EVM, WASM, ... So that's it. The language that your VM speaks, how it understands what the instructions mean. And we have a constraint system, which is expressed in some arithmetization like R1CS, Plonk, Air, etc., M3, if you know about that, and all of these sorts of things. And that describes, these constraints are meant to imply the semantics of the ISA, the instruction set, right? So if you have a Risc5 zkVM, you want a constraint system that is satisfied if and only if this is a valid Risc5 trace, an execution of a Risc5 program, right? So we have this ISA, we have a witness generator, which generates the execution trace, which a constraint system is meant to verify. And we have a prover and a verifier. We've talked about these a little bit in some of the previous talks, which are the two parties in this SNARK protocol where the prover takes in, both the prover and the verifier know what the constraint system is. The prover takes in an execution trace from the witness generator, and it generates a SNARK, which is a succinct proof, a succinctly checkable proof that the verifier checks, and hopefully the verifier will only accept this if the state update that the SNARK is attesting to is produced by a valid Risc5, EVM, WASM, whatever execution trace. So what are the security properties of these zkVMs, right? So all of these these pieces that we just looked at have all sorts of different security properties, which impact the three key classes of security properties that we want a zkVM to satisfy. So we have safety, which in English means, well, nothing goes wrong, right? So things like, oh, your zkVM doesn't generate a proof that's accepted for an invalid trace. These sorts of things, right? To be able to verify safety of the system, we need a bunch of things. So we need to formally verify the constraint system against the semantics of the ISA. So we need to say, hey, this constraint system, where if it's satisfied, this implies that this is a valid Risc-V trace, or this is a valid WASM trace, or whatever. We also need to know that the proof system is sound. So we have all of these different proof systems. DPALI is typically for a lot of the hash-based proof systems as a sort of like top-level snark that you have there, and you want to prove the soundness. And so this mathematically means, well, for every statement, so in our context of a zkVM, a statement will say, hey, there's a state update from state A to state B. If there doesn't exist a witness, so there isn't a valid execution trace that brings state A to state B. That's what this relation is. This R is a relation that says, hey, this statement is valid against the execution trace. So if such a witness doesn't exist, then the probability that a malicious prover that knows the statement can generate a proof P that the honest verifier will accept is smaller than some epsilon S. So that means that the probability of this is negligible, right? It's a tiny probability. This only happens with tiny probability. And the final thing is, so this thing here is a property of the protocol itself, right? This protocol itself needs to be implemented. So people write these provers and these verifiers in Rust, in Mule, all sorts of things. The final thing that we need to know is, of course, that the verifier implementations themselves are actually conform with the specification of the honest verifier that of the proof system, essentially. The second class of properties is called liveness, which means good things eventually happen. We also kind of want that. One of these things is a proof system completeness. So we want to say that if the prover knows a witness that satisfies a relation, so it's like a correct trace or whatever, then the prover will be able to generate a proof that the honest verifier will accept with all but negligible probability. And most of the proof systems we look at are what we call perfectly complete. So that epsilon C is 0, right? So we accept it that there is a proof of certainty if there is a valid trace. And then, of course, we want to prove that the prover implementation itself is correct. And because, of course, if the prover implementation is incorrect, we can have all sorts of liveness issues where there is a trace that the prover is not able to generate a proof for, it crashes, whatever, and that can cause a liveness issue if there's a block that just won't be accepted, right? That we can't generate a proof for. The final property is privacy, which is where we want these proof systems to have what we call the zero knowledge property. I'm not going to go into too much detail there, but the high level idea is that, and it's actually even a little bit difficult to mathematically formalize. It's possible, but I didn't want to put this in because it would just be confusing. When an honest prover and a verifier interact, the verifier can't extract any information about the witness. Right, and that means that the witness is hidden in a sense. But now that we know, hey, what are the security properties we want? Well, I'm going to tell you a tiny bit about what even is formal verification and why would I even trust this to tell me that the security properties are actually true. The first thing is that basically formal verification is a bunch of techniques that are used to ensure the correctness of software against formal specifications, right? And basically, typically what we do is we encode formal specifications. So these are smaller formal mathematical models of the intent of the behavior of the software. And we want to encode the proofs that the software actually satisfies these specifications into machine checkable forms. And there are broadly, this isn't entirely true, there are actually some other classes, but I'm not going to cover them here because, well, limited time. But there are broadly two high-level classes that of approaches to the making these proofs machine checkable. There's the interactive theorem proving approach, and there's the automated theorem proving approach. And the trade-off, hopefully, is sort of like kind of obviously described by the names. Basically, you try to give it a theorem you want to prove. You want to say, hey, this piece of software satisfies this, and it tries to automatically do it itself. Interactive theorem proving, where we use these theorem provers like Lean, Rock, Isabel, Agda, and many others, actually allow interaction with a human being to allow you to guide the writing of the proof, essentially, right? And the fundamental trade-off is, well, ITP takes longer, but is much more expressive, whereas ATP is much faster, but can only really verify relatively simple things. And when you're talking about the kind of properties that we're talking about here that require facts from coding theory, algebraic geometry, etc., to prove the soundness and completeness of these proof systems, well, you really kind of need to go to ITP. Okay, my team in particular, Nethermind, uses the Lean theorem prover. As I said, they will no doubt be sending a cease and desist letter to the Ethereum Foundation very soon. What is Lean? It's a theorem prover. It's also a programming language which enables you to verify programs in other languages, but also in Lean itself, and then extract them. It's a home of MathLib, which is the largest repository of formalized mathematics in existence. There's currently a £1 million project that has been funded by the British government to formalize the proof of Fermat's last theorem in Lean, and there's a huge amount of extremely advanced mathematics that is being formalized there. There are professional pure research mathematicians at universities who are currently using this thing as the trust base to formally verify their work. This talk is not about its impact on mathematics, it's about its impact on Web3, but it's sort of also very interesting about how this removes the sort of like typical trust base that mathematics has, where like typically if a proof is very complicated, I'm only really going to prove it if it's written by someone, like verify by reading it myself if it's written by someone I kind of trust, right? But now I can just like run a compiler and it will tell me, hey, this proof is true or not. It's based on the minimal dependent type theory kernel, which is establishes a shared standard of truth for all of these things, right? This kernel is reviewed by thousands of, well, even tens of thousands of mathematicians who use this thing every single day. Which gives us a very high degree of trust to the correctness of this, right? This is used by, I mentioned I'm name dropping a couple of people. Kevin Buzzard and Terence Tao, for those who don't know, are basically the two top pure mathematicians of our age. They're actively using this to formally verify their work. And so we believe that this is a solid trust base to verify the correctness of these protocols for Lean Ethereum. I'm going to give you now a very quick overview of the existing work to do this for the verification of the constraint systems, and then we're going to talk a little bit about the rest. We have formalized systematics for a bunch of things. There's a Risc-V specification that was extracted from the sales spec, which is, well, that's meant to be capitalized, another small typo, this was work done by Galois. So we've extracted the official formal specification of Risc-V into Lean. We have formal EVM semantics, which actually my team, one of them my team maintains. This is the EVM UL Lean spec, and then there's also the KEVM spec. These are the only two specs that are fully compliant with the execution tests. And there's also a formal WASM specification as well, but yeah, that doesn't matter too much. We have all sorts of tools for extracting constraints from various DSLs that you can see into various proof assistants like Lean. There's also Picus, and there's a bit of Rock somewhere. There you go for Plonky 3. So we can extract all of these constraint systems into various proof systems, theorem provers, to formally verify these constraint systems against a formal spec. A very quick overview of ongoing work. So there's a Certiplonk framework that we're working on, which we just talked about, for formally verifying ZK circuits written in Plonky 3. It allows us to extract Plonky 3 into Lean. We have a formal model of errors and interactions, so lookups and permutation arguments. We have a Grubner basis solver, which allows us to try and automate the verification of whether a system of constraints is deterministic or not. And we're working on formally verifying a Ketchak 256. We've been working with a bunch of companies to formally verify their constraint systems against this formal spec. So SP1, amongst others, we've actually formally verified their Risc-V ALU and memory constraints. We've actually verified them against the formal Risc-V spec. We worked in the past on the Scroll zkVM, trying to verify the Ketchak 256 circuit. We found a very critical bug that allowed you to prove that Ketchak of any value was equal to any value. That's pretty bad. There's some work on extracting Plonky 3 into other proof assistants. This is meant to be Rock, sorry. Other proof assistants by Formaland. And there's also this LLZK work, which is meant to be a sort of a universal IR for ZK circuits, so that we can formally verify them. And to finish all of this off, to tie all of this together, we have all sorts of work on proof system verification. So we've just worked on actually completely trying to create a blueprint to formalize the security properties of Fry in Lean. And there's some other work to verify SumCheck. And then Stir and what is actually meant to be on the next slide, it's like future work. As I said, to tie all of this together, the idea in the future is to have extractions of Rust-Interlean, and we already have extractions of EUL-Interlean to try and actually verify implementations of the underlying cryptographic protocols against all of these formal models that are proven to have all of the nice security properties we want. We want to verify all of the, not only Risc-V, but other zkVMs against the full semantics. We want to continue formalizing more proof systems. As I said, we're already doing lots of people talked about like multilinear proof systems like WER and these sorts of things that we want to formalize the properties of in the future. And as I said, we want to really be able to extract the provers and the verifiers to be able to verify the underlying ZK proof systems. Thank you very much. Yeah, and some conclusions that I'll just repeat the things. I'll just skip directly to questions if that's okay. Thank you so much.
It's a very quick one. You talked about safety aliveness properties. Are the privacy ones like hyper properties? Can you talk a bit about that?
Yeah. So they are hyper properties because they are linking you have to explain a link between the trace of the verifier and what is known as an extractor, right? So like typically the privacy properties are formalized by saying does not exist an extractor that can see that can sort of sorry, I'm thinking about knowledge soundness. Sorry, let me think about that again. Is it a hyper property, the zero knowledge property? Because no, it isn't quite, right? Because actually what we're saying is that all adversarial verifiers could not extract extra information. So it isn't, but specifically the knowledge soundness can be phrased as a hyperproperty. Thank you so much.